I'll be giving this tutorial. Lessons learned as a small network operator, things I've picked up on through various different NANOG presentations that have made a huge difference in life as a network operator. Agenda of what we're going to cover. Hopefully these slides are up on the website by now. Overview and background of where I'm coming from, basics of our POP architecture, a focus on IGP, followed by BGP, then MPLS traffic engineering, some pointers on monitoring, and a few other random items from there. So email address is there. If you have any questions afterward, feel free to track me down and ask whatever you'd like to know. Up until basically last month, maybe even this month, I was in a hybrid engineering and ops position for a small telecom and ISP in Texas. We were recently acquired, so now I'm strictly in the engineering department. This, in a sense, has increased the traffic that I deal with by a factor of 6. So we'll see what all changes going forward. General objective when you're doing network design, keep things simple. Dave Meyer said somewhere along the line, be realistic about the trade-off between complexity and operational expenditures. And I simply say be realistic about your network complexity no matter what. If it's simple, it's easier for various people to troubleshoot. If it's simple, the network will scale. And if it's simple, you can go to NANOG and take other vacations without a lot of stress. Whenever you're doing engineering, troubleshooting, or anything to do with your network, think like a router. Think through how will this router deal with packet processing sequence? How will it forward this packet on a packet-by-packet basis, and then work your way through your network on a router-by-router basis. As I coach NOC people and other operations staff on how to figure out what's going on at this moment, this type of analysis comes in very key for them. So 6 years ago, came into a job working with 4 routers, just 1 router per POP. DS3 is tying it all together, but we're doing a whopping 5 megabits to the internet. Over the next 3 years, we grew to 35 routers, lots of DS3s, 200 megabits total, and we've slowed down since then, but it has grown another 50 megs at peak. We're back down around 200 recently, but that's about where we're at. 4-city network. Our internet pipes were just 4 T1s to cable and wireless. Cable and wireless statically routed to us. We had default routes. Everything within the network was static. And corporate offices were getting to the internet through a pretty scary process of NAT. And those 4 routers in the POPs were Riverstone, which nobody knew. And this was a challenge from a support perspective, from a design and architecture perspective, and even BITIS from a sales perspective. Salespeople would get asked the typical question, are you guys using Cisco or Juniper? And they'd have to say, no, we're using Riverstone. And the customer would follow with, who's that? So we started planning our upgrades after we ran into flow routing limitations of the Riverstones. And everything you're going to see in the rest of this presentation is what we use to get us to where we are today. So whenever you're looking at your router, obviously any network pretty much starts with 1. You might run out of slots. You might run out of memory. You might find yourself tapped out on CPU resources as you plan to upgrade. You're going to find that you need to become an expert on the different routers you may select. We learned very hard that we had to become quite well versed in memory errors on Cisco VIP2s. Once we learned them, we knew whether it was bad memory or bad VIP. We knew what had to be replaced, and we were able to get past our problems so that it didn't recur and impact our customers going forward. We continue to learn about implications of different GSR engine revisions and continue to get bitten by little limitations in Catalyst 6500 line cards. And those wonderful concepts of redundancy. Everyone wants to hear that you have a redundant network, and multiple routers don't ensure that you've got redundancy. Proper design using those routers is key. If you've got one router in service and you decide to add router 2 as merely a child of router 1, router 2 is completely dependent on router 1, and you've made things worse, not better. So our initial design involved a two-tier model, essentially a upper layer that handled all the interconnections between sites and also our connectivity up to the internet. We continue to be fed merely by transit connections. The lower tier, a distribution tier, handled all of our customer connections. To some degree, we aimed for distinct routers suited for particular connection types. Ideally, and this is where we're heading, it wasn't this way in the beginning, one type of router for fractional and full T1s, another type of router for DS3 and larger WAN technologies, OC3 and so on, and then one type of router for Ethernet services. So looking at our initial core design, to tie all these routers together, whether, obviously 2 core routers per city based on our redundancy goals, and then 1 or more customer connection routers. We used 2 parallel LANs to tie these together. So 2 separate Ethernet switches to provide essentially backbone redundancy. Each of the core routers connected to both LANs, each of the distribution routers connected to both LANs. And that got us going. It started in our first POP and continued thereafter. And here's a representation of what we had. So all the different routers became pretty much similar icons within our model, 2 switches to tie it together. But we soon ran into issues that the routers, because they're going through a multi-access topology, wouldn't be able to detect when another router lost a link, had a card fail, or what have you. So there'd be time, we'd have to wait for IGP timers to time out. And we had not yet explored much with tweaking those timers. Regardless, I don't think we could have gotten down below 3-second failure detection, and we weren't real happy with that, especially because in the default case we were looking at 40 seconds of black hole until we detected the failure. Likewise, capacity issues. If the links from those Ethernet switches to the various routers were fast Ethernet in some cases and gigabit in other cases, the sending router would not know of a bottleneck going to the receiving router if it was transmitting on a gig link and draining out a fast E-link. And likewise, we had troubleshooting issues. We had a lot of round-robin packet delivery, especially in the case of a link failure, quite unpredictable as to what the path would be from one router to another. So, as part of hardware upgrades, putting GSRs in the core, we worked on transitioning our topology so that the core routers connected to each other, so that transit traffic had a direct path, and then the core routers connected to each distribution router. So even though essentially all were Ethernet, we were able to treat them all logically as point-to-point links, and that gave us a lot of gains throughout our topology. So here's a representation. 2 cores talk to each other. Everything else connects merely to the cores. So now the core routers know link state to all the other routers, and vice versa. And routing became more predictable, and our queuing became more predictable. Got us going, gave us what we were looking for, but got bit by another challenge then, because our upstream connections were on those core routers. So obviously we're so far a Cisco-only shop. Within iOS, the BGP path selection algorithm, rule number 9, says prefer the external BGP path over the internal BGP path. And therefore, interpop traffic that might be coming in from an adjacent POP and then heading out to the internet would leave by the logically closest link unless another link was drastically better. So here's a representation. The 2 routers in the center are, we'll call it City 1. Each one has an upstream internet connection. And you'll see City 2 on the left and City 3 on the right. And traffic coming in from City 2 wanted to leave by way of Core 1's upstream, since it was an external BGP path. City 2 might have originally chosen a best path from Core 2, but since each router is making its own routing decision by doing its own layer 3 lookup, Core 1 sends it out upstream. So here's what we were hoping to have happen. City 2, through its full IBGP mesh, had selected Core 2's upstream as its desired exit point. Let me show you. Here's what we were seeing as a result. The traffic coming in from City 2 was instead going directly out Core 1. And the reason for that is Core 1 prefers most paths out its external path, and Core 2 prefers most paths out its external path. In City 2, those core routers were learning both paths by a BGP full mesh, and its core routers were selecting a best path as City 1 Core 2 for one reason or another. Most likely oldest route, perhaps a router ID. It all depends on the individual situation. So City 2 was sending packets destined for that internet destination towards City 1 Core 1 because that was its next hop towards City 1. And so as the packets arrive on City 1 Core 1, another IP routing lookup is performed on the packet, and it decides that its best drain point is the upstream link rather than sending it over to Core 2 in that same city. So that's how we ended up with this challenge. And because of our traffic patterns, customer differentiation between markets and so forth, we found this incredibly difficult to tune. As we grew, we found that our upstream links, typically on 2 or 3 year contract terms, were becoming increasingly difficult to balance well when traffic was coming in from another city. So we kept our 2-layer hierarchy, but split that lower tier into 2 types of routers, one for customers, and still tried to break that up into connection-specific choices, and then added edge routers, which were handling specifically our upstream connections. So essentially an upside-down V when you look at an architecture. Redrawing our core and edge challenge, we've added in edge routers as a separate layer from the core, and now traffic coming in from City 2 arrives on Core 1. Core 1 can make a best path decision. Both of the drain points are external, so that decision does not factor in. It probably falls down to oldest route and can now choose to send it to the right edge router and go out that connection. And it was, for us, a fairly small CapEx in order to realize significant operational cost savings, because we didn't have to upgrade pipe sizes just because of an inability to tune them, knowing that another pipe might end up becoming less used due to its term length. So split the upstream and downstream roles and remain with the topology where each distribution router and each edge router only connects to the cores. There was an alternate fix that we ended up upon as a result of deploying MPLS in the backbone, but didn't know ahead of time that this would have fixed it for us. Had we deployed MPLS upon the packet coming in from the customer heading towards the internet, that inbound distribution router would have done its own IP lookup, having full tables on hand, and would have found the best egress point and potentially even interface, and would have applied a label corresponding to that exit point. The core routers all throughout the middle of the path would have forwarded solely based on label directly through Core 1 and hopping it over to Core 2, and then Core 2 would have done its egress decision and sent it out that direction. So, on to selecting an IGP. 4 choices. We ruled out RIP v2. It needs to be dead. We were running Riverstone, so that immediately eliminated EIGRP, and gave us 2 choices, OSPF and ISIS. And perhaps selfishly, but since I was the one who was tasked with putting in some form of dynamic routing, our selection was OSPF, considering that at the time we were completely statically routed. The person who had been maintaining the network prior to me, whenever there was an intercity link failure, would hop into routers through backdoors and console connections and do static routes to patch around it. And inevitably, through whatever magic he was using to pick those static routes, when our internet connections came back up, those particular affected cities were black holed again until he removed all of his Band-Aids. So over time, we switched to ISIS. 3 supposed benefits. Stability, on the premise that the various hardware and software router engineers were being very careful with change management in their ISIS code. Can't really say that gained us much of anything per se. Protection, in that there'd be no CLNS packets coming in from customers or providers. And thirdly, as we began to roll out MPLS VPNs with a suspicion that our customers might request dynamic routing with us and that they might ask for OSPF to do so, we wanted to separate our customer-facing VPN dynamic routing, router OSPF blah, from our production network IGP by doing router ISIS, so that people wouldn't accidentally go into router OSPF1 and blow something up when they meant to be on a VRF on a different process. Turns out in the 3 or so years we've had VPNs that none of our customers have requested dynamic routing. The only customer with it is us ourselves for corporate offices. And that was BGP until recently. We've now switched to OSPF. The assumption is that staff won't be blowing that up between corporate and production. And because of a variety of reasons, primarily IPv6, we've switched back. Did the rollout as part of our IPv6 rollout, which will be in another presentation at this NANOG tomorrow, but also chose to do it because we had forecasted a use for gear that did not support ISIS whatsoever. So by rolling back to OSPF, we were able to keep our topology and architecture consistent. The typical IGP design goals that you hear in a lot of the other NANOG talks but are consolidated here: keep everything lean. Device loopbacks, links between devices, nothing else. I've even heard of people taking their inter-device links out. Haven't quite figured out what they're after and how they're doing it, but if it works for them, even better. Everything else belongs in BGP. It's a protocol made for thousands of routes, and it's got administrative control and plenty of filtering capability that's specifically not in OSPF. And we copied a lot of the work of VJ Gill and the AOL Transit Data Network team from their NANOG 29 presentation, I believe, from when they converted from OSPF to ISIS. We used that during our conversion to ISIS and copied the metrics coming back to OSPF more recently. Doing so, we started with a table of metrics based on link rate and then add a various modifier depending on the role of a particular link. So our general table goes from 1 to 10 for OC768 or 40 gig Ethernet down to DS1. Considering that our total traffic right now prior to acquisition is a quarter gigabit, I'm not real worried about anything bigger than that, whether it's 100 gig, 160 gig, or whatever. Modifying those metrics. The links between cores are metric 1, no matter what size the pipe actually is. On rare occasions, we've had 2 different sizes of pipe, one a primary, one a backup. So the primary would be 1, the backup would be 2. Links from core routers to distribution routers are 500 plus whatever was in the table. Links from core to edge are the same, 500 plus whatever's in the table. Links between cities so far are 30 plus table value. I believe VJ and the ATDN folks mentioned that they have different levels of modifier based on whether those links are within a region, cross regions, or cross continents. This will be a matter of study for us as we move to a multi-state network post-acquisition. TexLink is based in Texas, and PacWest being based in California, we may have to do some semi-separation between the two until we get upstream links rebalanced and whatnot. And as I'll highlight later in the talk, we've had to do some minor tweaks to these WAN link values based on BGP tuning purposes, considering that one time, not thinking through all the implications here, I managed to blow up an entire POP when multipath ran all 4 customer connection routers out of memory at the same time. Considering it was also the router that handled our office, it was a bad day. Every now and then, staff need to do modifications to the network, whether it's planned maintenance, upgrades, downgrades, what have you. They've all been told add 10,000 to the link cost, and that way it's pretty easy to figure out what the link is supposed to be when they're done with their maintenance. So if we've done some changes, and let's say there's a DS3 that would have been a metric of 38 because it's going between cities, but for tuning purposes we may have made it 43 temporarily. They know that when they see a link cost of 10,043, they should revert it back to 43 for simplicity. If for some reason a link really should not be used, the delta is 20,000. Folks usually tend to go, Pete, why is this one 20,000? And that's enough time to say, whoa, step away from where you are, and let's not disturb that right now, and here's why. So, with the carefully engineered metric design, we get a very predictable traffic flow. And that's good both under normal conditions and when a link is out of service, expected or unexpected. And I diverge for a moment to say learning the algorithm by which the routers select paths will really assist in understanding what's going on. My magic light bulb came from the book shown there, Traffic Engineering with MPLS. And I gave a tutorial back at 37 about traffic engineering. And in there, there's an exercise that explains both the base shortest path algorithm and also how it works within traffic engineering. So, key factor in the link design and metric design is that our distribution and edge routers aren't necessarily sized to handle traffic that for one reason or another is trying to transit this POP. So far, our network isn't big enough in a steady state configuration to have much, if any, transit traffic. But we had a link outage over the weekend as I was arriving here in Dominican Republic, and we were punting all traffic that would normally have go from Houston to San Antonio through our Dallas POP. So that extra traffic, were it to have tried to travel through the router designed to handle customer T1s, could have put a serious hurt on that poor little 7206. So we want to make sure that the traffic that in this case is transiting core-to-core link knows where to go. Had the core-to-core links in Dallas gone away, we would have been in a bad space anyway. But let's say those are the only 2 links that were down. We want to make sure the traffic that otherwise want to go through them will go around the WAN rather than trying to punish our customer distribution routers or our upstream routers. So to do that, we know that the distance within a POP, going from a core down to a dist back to a core, or likewise core edge core, is going to be at least 1,002, because those link metrics are always 500 plus at least 1, and likewise 500 plus at least 1. Whereas the cost to go around the WAN is always going to be at least 63. Since from this city to the next city will be at least 31, 1 to go from core to core, and 31 to go back through another WAN link to this city. If there are additional cities going around that ring, the WAN cost is going to increment by anywhere from 32 to 40 per city. So in this case, traffic would rather go through 23 cities before it would decide to go through the distribution layer, keeping us safe. For now, with only 4 cities, we're safe. But I know that we're on an expansion roadmap, and I'm very happy that I'm not going to have to go back and recalculate and re-engineer for a long time. So here's a representation of those metrics, not totally to scale, but you can see that the distance from core down to distribution and back up again is far greater than it is between the 2, or particularly to go over to another city. And as our staff begins to become familiar with this, they get to see that it truly is consistent. As long as they've got the metric table in front of them, I've occasionally given them projects to configure a new router being added to the network, and they can understand better how to put in the proper configuration entries. So the event that kind of bit us that one afternoon, we have links to NTT Vario in both Dallas and Houston. And based on the BGP path selection algorithm, rule number 10, prefer the route that can be reached to the closest IGP neighbor, lowest IGP metric. Core 1 in San Antonio was connected to Dallas. And in Dallas, we had a link to 2914. And therefore, San Antonio Core 1 liked to go that direction. San Antonio Core 2 was connected to Houston, and we had a link to NTT there as well. And Core 2 liked to go towards Houston. We noticed that some of our Dallas distribution routers were sending outbound traffic over to Houston to go to NTT because of a difference in IGP metric from Dallas distribution to Dallas core to Dallas edge versus from Dallas distribution to Dallas core over to Houston core and then up to Houston edge. So we tweaked the link metrics going from Houston core to Houston edge 1, rebalanced traffic, and sure enough, those Dallas distribution routers began doing the thing that we'd hoped they would do, and that was to stay within city and send their traffic out to Dallas NTT. However, our San Antonio distribution routers had BGP multipath enabled, and they were now getting best paths, at least if they were headed towards NTT, pointing towards Dallas from Core 1 and pointing toward Houston from Core 2. So for 40 or 50,000 prefixes, we now had 2 entries, and those poor little RSP4s all went boom pretty much simultaneously. And considering that my desk and all of our support personnel were behind one of those, we were kind of in the dark until we figured out maybe that change about 10 minutes ago was bad. So our retrofit was merely to leave the Houston edge metrics the same, or as desired, so that everything matched and behaved similarly between Dallas and Houston, but to change the WAN links from Dallas to San Antonio and Houston to San Antonio. So the San Antonio core routers had a clear preference, I think currently it's towards Houston, and wouldn't feed the distribution routers with a multipath mess. So within BGP, it's made to scale. Use it. We carry all of our customer link subnets, customer LAN subnets, and external routes within BGP. As well, it's got great filtering tools. Use them. It'll save your life. We filter at every route ingress and route injection point. And in doing so, we apply an internal community so that any BGP route anywhere on a network will have at least that internal community. So from a troubleshooting perspective, we're able to figure out where it's coming from instantly. You're going to have to scale your BGP at some point. Confederations did not work well for us. We started off using 1 sub-AS per POP. When you have 1 router per POP, it means each router is its own sub-AS. Convergence was painful because those POPs would end up having to send a full table over to their confederation neighbors as opposed to in a route reflector situation where they send only best paths. And if they're getting learning routes from an adjacent POP that were better anyway, you've got a much simpler reflection upon BGP session restoral. So in the process of doing our various POP upgrades, we removed the confederations and deployed route reflectors in the step-by-step process. And again, following the suggestions of VJ Gill and ATDN, we have no client-to-client reflection. The distribution and edge routers within a POP are fully meshed, which theoretically prevents at least first layer med oscillation. We are nowhere near hitting that, but I'd rather take the future view now than have to go around later and race around and fix things up. So within our distribution layer, all the customer links are redistributed into BGP as connected routes. Make sure you exclude the interfaces that are from dist to core. And we got burned on this once when we didn't write our route map. Or I suggest that you don't write your route map to exclude by interface name. If the router comes up and the VIP is not there, it'll drop out that reference in the route map. And now you instead of denying one interface, you're denying all routes. Instead, use a prefix list so that even if you end up with no interfaces matching that prefix list, you have a static reference and you won't have this kind of black hole. Likewise, we redistribute static routes into BGP. May want to consider a prefix list there to make sure you don't capture any private space you might want to block. In doing so, when you add a customer to a distribution router, you don't need to go anywhere else to make sure that they're properly routed. Scales very well. It means that a lot of your technicians will only have to deal with the distribution layer and won't have to deal with much of your redundancy and scalability. BGP local pref design. This is one of the magic secrets that I've never found in the books, and sometimes you can't even find it in many of the NANOG presentations. You want to choose your local pref values so that traffic goes appropriate to your dollars, knowing that transit probably costs you money, peering might cost, might not, but perhaps lower than transit, and your customers mean revenue. Makes more sense to send traffic to a customer than it does to send it through one of your transit connections, and most people seem to be using local pref to accomplish this. So our basic design, although not totally reflected in all of our routers, is that customer routes are given a local preference of 400, peer routes get a LP of 300, transits are 200, and any route that temporarily is being asked to be treated as a backup to some other customer peer or transit route gets a local preference of 50. Since the routers default to a local preference of 100, if you forget a route map or you typo a route map, you're going to have routes that are invisible. And you're going to go troubleshoot it. And you're going to go, oops, I forgot or I bombed a route map. And you're going to fix it early rather than crashing into it months or years later. And as everyone requests, please filter your customers. We do it once on ingress from our BGP customers, and we do so very aggressively. For each prefix, we check that prefix against a prefix list and against an AS path list. We allow that customer to prepend as much as they wish. We allow them to truncate the AS path. So if they have a customer of our customer that's giving them a prefix, so we might be seeing 2 different ASs in the path, we'll allow our customer to take over that route for their customer in the event that their customer has some sort of emergency. So the second and subsequent AS in that path is completely optional. We tell our customers about these rules and a whole bunch more at turnup. And assuming they read the document, which we've noticed they do not rarely do, they have everything they need to know to bring up that session without a single phone call. We also factor in no routing capability, and we do so somewhat with a certain amount of complexity, but the reality of it is it gives the customer flexibility and allows them to do a lot of stuff without ever having to call us, assuming they have enough clue to use it. We'll accept their aggregate routes marked for null routing. We will treat internally as a null route, and we will propagate those aggregate routes, allowing them to do certain tricks, which we'll cover in a bit. And certainly we'll accept their aggregate routes, assuming no tagging, or at least no null route tagging, and propagate it normally, as would be expected. We will accept any more specific of their aggregates marked with null route. We will treat it internally for null routing. We will mark it internally for no export so that it doesn't go out to providers and customers, since it most likely would get filtered anyway. Shared all within our network. We do also accept more specifics of their aggregates if they mark them with an override community. We treat that as an aggregate and allow it to be propagated out on the hopes that our transits filter on a less than or equal to 24-bit basis. Obviously, that's best effort for some of our upstreams, but the notion behind this for a small shop such as ours is that if you have a customer with sufficient BGP clue to call you up at 7 p.m. on a Friday night and say, hey, I just added a customer 2 minutes ago, which we know is false, but they've got this new prefix they've brought from wherever, and they want to be able to route it. We'll say, go ahead, put 11457:20 on that announcement. We'll accept it. We'll propagate it, assuming it's somewhere within their prefix list, and allow it to go out, and hopefully it'll magically begin working. We expect that it will for at least one of our providers based on current patterns, and allows us some time over the weekend or Monday or Tuesday to do the right thing and get those routes added properly to our filter list. Last but not least, we will accept more specific routes of that customer's aggregates untagged. We'll accept them, we'll mark them as no export because we see no reason to send them out. We'll propagate them internally. We use it as a anti-spoof filter opening for traffic engineering purposes. A little bit complex, but it means that life is very hands-off for BGP customers. So basic thought is the customer can obviously announce their aggregate route. They can announce that aggregate route and null route some specifics, which we figure is the second likely case. If they have enough clue to use null routing remotely, they can accomplish it themselves. They also have the power to announce their aggregate and null route it, which we'll propagate externally, and also announce more specifics without null routing tag, for which we will forward to the customer. So let's say they have a /20, only wish to use the 24 of it, they could announce the 20, null route it, announce the 24 to us. The rest of the 20 gets black holed for them very easily. They don't have to do the other 15 /24s to be null routed to get to where they're going. They can do it with 2 announcements. And within that 24, they could null route further specifics. So it's a very scalable, hands-off design, keeping the customers off our phone lines, out of our hair. Here's a sample. In this case, they've got a 22 of our space. They've marked it for null routing, which is the 11457:0 or null. We accept it, pass it out to the world, and null route it. They can also announce the 23 within it. We'll accept it, share it within totally internally, route it to the customer as would be otherwise expected as an RPF opening, and they can also announce a 24 within the 23 and null route. And in doing so, they've got a 22 with only a 24 forwarded. So very hands-off. If the customer has enough clue to even null route, they might want to do this. Wasn't too hard for us to write in the beginning and continue cloning for new customers, and scales very well for us. One side challenge is that for every customer, we have at least 2 prefix lists. One that's the exact match on their aggregate routes, another one that's LE32 to allow them to do their null routes and their overrides. If the customer asks, we will adjust their inbound route map to inject various tuning communities at their request. We've had customers that just don't understand how to do a simple route map to set a community, and we'll do this to get them out of trouble. Going back to the internal community design, we tag every single prefix internally the moment it becomes a BGP route. In doing so, we identify the POP where it came in, a general requested exit handling, and a type of route so we can interpret where it's coming from and what it's being used for. One of the things that we do with that is to use the POP of origin to adjust MED automatically. It's a simple geo-routing, and it's saved significant city-to-city WAN costs and link sizing for us. Design is our AS :ABCDE. First digit is the route type, customer, ours, or upstream. BC covers up to 100 POPs. So far 5, but we're about to add 5 more as part of the acquisition. D is a high-level desired tuning. 0 is based on whatever we've cooked up over time to keep links balanced. 1 pretty much strips out any of our tuning and goes to whatever the providers would give us if untuned otherwise. 2 is for backup and 7 is for maintenance. And the last bit indicates what to do from a geo-routing perspective, whether to apply meds or not. So here's a sample, 11457:10200. Since A is 1, it's a customer route. Since BC is 02, in our case it came from POP2, which is Dallas. D is 0, so we propagate it based on whatever tuning we've cooked into our existing route maps, assuming that, and there's no hook out to avoid them. And E is 0, so we announce it as hot potato, which is a default med in all cities. The geo-routing for us is very simple. I have a suspicion it's going to grow to maybe a 3rd tier. Right now it's basically near versus far. If that internal community matches 11457:4 dots and a 1, last digit being 1, and it matches a nearby pop of origin in BC bits, we set med to 200. If the internal community matches 11457 and then ends in a, oops, I have a typo there. No, that's right. If it ends in a 1, but it's not matching a BC of a nearby pop, med is 400. If the internal community ends in a 0, it's going to get med of 200, whether near or far. Extending that BGP community design, develop a set of communities so that you and or your customers can apply to those routes for tuning within your network. We allow our customers to do, obviously they're going to default to customer level local preference. They can choose peer level local preference or backup. If they want to do if they have 2 connections and want to do a customer versus customer backup or peer versus peer backup, we tell them they can do so using local, meds within that level and local preference to get between customer and peer. A little bit more complex than using the heavy hammer of local preference, but it's more scalable and keeps our route maps cleaner and our local preference count cleaner. So for the simple stuff, 11457 colon 200, 300, or 400 is the customer, peer, or transit levels, or other way around, and of course the colon 0 for no routing. We have another set of communities that we or our customers can apply to routes for tuning outside our network. In this case, it's for our upstream providers. We do not yet have any peers, but this would scale to those as well. We can mark prefixes for no advertise, whether to one provider or all. They can set prepends to those providers that are independent of whatever they might announce into us, and they can also request local preference. So here's a diagram of our tuning logic. As it leaves our network, we filter out any other upstream routes. They have no sense going back. We don't want to be a transit provider between our providers. We allow routes from customers or our own flagged with individual or global local preference or prepend requests. And this does get a little complex to handle multiple combinations therein. If we've had any of those requests, we then hand it off to the final logic that does the med selection. If there were none of those requests, we allow routes flagged with internal local preference request and map a corresponding external local preference request. If there's nothing there, we process routes based on their embedded tuning, that D bit within the internal community, and likewise hand it off for meds. One of the things we've found the hard way in the beginning is that if a customer through communities or other route map tuning ever requests to be treated inside our network as a peer, it becomes essential to announce that prefix outward as a peer as well. Otherwise, you end up with a certain stickiness that if they ever fail over to us, external routing will then glue to our transits, and when their primary link comes back up, our transits still like the route coming from us because they see it as a customer route. They will stick to us until the customer breaks their link with us, causing additional pain, flap dampening, etc. So using those meds for geo-routing, we quote-unquote enjoy parallel connectivity to 3 different transit providers. For each of those providers, we have a link to that network in Dallas and a second link to that network in Houston. So for outbound routing, we receive those providers' routes and their customers' routes and rely on the meds learned from them. Most likely any other routes we learn are peers. Perhaps they are purchasing transit. I'm not certain about one of our networks. Regardless, we zero out the meds on anything we get that's beyond them that's not a customer route. If they can't give us much direction on where to send it, no sense us trying to send it through multiple links of our own. And it works well because in normal state, cold potato, sending it straight out to them, or sending it through a preferred med value is only 1 hop longer than hot potato, sending it straight out the local city. And the assumption is we know our network. We know we've done very careful IGP metric design. It's working for us. We know that we've chosen good backbone networks. We assume they've done a lot of careful IGP metric design and so forth. But we know our network better than we know their network. We don't know what they use for med values, how significant they are, if there's a way to add to them. There's certainly no way to multiply them within our route maps. So if they're telling us that a particular POP is better, we will use it, but only on their routes and their customers. Because the assumption is the med learned is in some way tied to IGP distance, fiber kilometers, some other vector towards wherever that particular prefix is going into their network. So if it's, let's say, one of NTT Vario's aggregate prefixes, I think they got 157, 229, or something like that. We know they're going to originate it on some subset of their core. We assume that that is going to be announced to us in Dallas and in Houston with some representation of how far it is to that particular injection point. For their customers, let's say they have a customer in Atlanta. We know that that customer is most likely better reached through Houston, which is geographically closer to Atlanta, than Dallas would be for us. So if they're giving us med, it's probably tied to that distance or some other link cost like that. And we'll choose to send that traffic through our network to Houston to give to, in this example, NTT, and let them carry it to Atlanta to go to the customer. So we feel that it's a pretty good balance between trying to do the right thing internally and trying to try too hard and send traffic all in funny circles. So obviously we have numerous customers that do BGP. We respect that many, perhaps even all of them, have little to no BGP experience. Most of the customers that we've had that were doing any sort of multi-homing were doing so merely for the sake of transitioning from old provider to us. And they perhaps had an ARIN assigned prefix block and felt that it would look best on the internet if they were announcing it from their own AS, when in fact we know that doesn't really matter. As long as that customer sends us just their aggregate routes with a reasonable AS path, and they don't dump their entire table, or at least so many that it bumps up against max prefix, everything works fine. If the customer requests, we'll apply reasonable tweaks. We've often had customers who had a link to us and a link to a tier 1 and find that a lot of the traffic comes in through us. We'll often mark their prefix to be treated as a peer in our providers, which tends to rebalance things well. Otherwise, we tell them, look, here's a web page with all of our current communities. You can do it with BGP route maps on your own end at whatever hour you want to do it. You never have to call us. And the few folks who've had enough clue to try and use that have found they've got all the knobs they need, even in us, a perhaps tier 3, totally transit-dependent network. Moving on to traffic engineering. Redundancy, especially in a small, minimally meshed network. 4 cities for us would theoretically need 6 links for full mesh. We've got 5. We do some subset of regular simulations, but it's not very conducive in our case to efficient redundancy. Favorite quote of mine from G.I. Jane, 2 means 1 and 1 means none. If you've got 2 links, you can fall down to 1, but if you have 1 link and it fails, you've got nothing. Unfortunately, 2 to 1 means half your capacity ends up being excess. We are such a small network that in many cases we've got to go with 2N redundancy to have any redundancy. Yuck. Getting around this based on multiple DS3s running between certain key cities, then multiple OC3s as we grew. MPLS traffic engineering saved our network. Normal IGP routing is completely unaware of traffic saturation until there's so much traffic that those keep alives go boom, and in that case you're in a very bad situation anyway, but it's just messy trying to send traffic a long way. MPLS-TE enables our routers to spread our traffic over multiple paths, including those that are not on the shortest IGP path. So we've often used, call it backdoor paths through Austin and through San Antonio, which were secondary POPs aside from our main Dallas and Houston sites. And it's done using one-way tunnels between routers. Initially, we had a full mesh of tunnels between all of our distribution routers and all of our edge routers. Sometimes one, sometimes two tunnels in each router pairing, depending on traffic loads. We ran very aggressive 15-minute automatic bandwidth rescaling timers, so those tunnels rapidly reflected how much traffic they were actually carrying, and those tunnels would then redistribute their traffic across the backbone very rapidly. And because we often had 2, 3, sometimes 4 DS3s over the primary path, and in some cases 120 megabits per second, maybe 140 megabits per second, trying to traverse those 4 DS3s, it was a very tight fit. It was the only way we survived. But we got squeezed because we had a customer who set up a news server, and those news feeds would get glued to a tunnel. So our best bet in these cases were to add more tunnels over particular edge distribution pairs. We went to 4 primarily to get traffic to hash over multiple tunnels. We knew that that NNTP flow would fit to one tunnel, and hopefully almost all the other traffic running from edge to dist and dist to edge would pick the other 3 tunnels, which pretty much did. Gave us the granularity necessary to rebalance all of that traffic. And the flip side is that all of our redundant capacity, backup paths, longer paths, what have you, can easily get used by accident because you don't really have an easy metric as to how much of that excess capacity or that excess traffic is traveling around a non-shortest path route. You can end up with quick surprises when your redundancy just isn't there. However, that excess capacity can be used during momentary surprises. We've had a few customers, still have one, that just seemed to be a bit of a magnet for DOS attacks. And when they would get DOSed, at least the network would take care of itself. We'd use up all available redundancy for that event, but at least we kept running. And the rest of our customers are not so severely affected by that DOS attack. Long term, we ended up with iOS version mismatches on different routers, and something just wasn't right. We could never get Cisco TAC to identify what was truly going on, but it just wasn't working. Knowing that our core is entirely GSR, almost, we migrated to just using MPLS traffic engineering over our WAN links, which natively were our smallest links and the ones that were the most likely to need protection. Each link gets 4 tunnels. So therefore, if one of those tunnels has to find a less than shortest path way from point A to point B, only about a quarter of the traffic over that link swings at a particular time, and therefore the traffic follows the shortest path, except in the face of congestion. And so we stay back to as close to simple as we can, predictable, rarely have to explain to people why traffic's going the long way, but it does happen every now and then. But it keeps us back towards a very default traffic flow most of the time. Changing topics to network monitoring. Obviously, we all have small budgets for tools. Consider taking off-the-shelf stuff and kind of home brewing some tweaks and modifications onto that. And do what you can to put information in front of your support folks, your NOC, and your help desk and whatnot. And perhaps you won't even have to share enable that much with your NOC folks because they'll be able to figure out what's going on a lot quicker. Our analysis said there were 3 problems to solve. Right now, what is up or down? That's perhaps what you might use What's Up Gold or HP OpenView for. An analysis of what happened when, whether it's simple with syslog or I'm sure there's other tools that capture that and show what's going on. And then how many bits, packets, errors, what have you, are flowing through the network. Obviously different tools to solve each problem. The 2 biggest things for us were MRTG, to be able to figure out what our trends were and what our traffic was. and homebrew enhancements that really tuned it up and made it useful for our people. And then syslog to show what's happening right now on the network. The MRTG that we've deployed has simple links on each customer-facing port for a cutesy network diagram, a link to be able to telnet to the CPE, and a how-to guide on how to configure our standard CPE, so that if we provision the customer port anytime during the day, tomorrow morning at 6 a.m., all these tools get updated and created, so that as long as we do it a day before the technician would be configuring the CPE, he doesn't have to ask anybody. It's got step-by-step with IP address values and channel assignments already coded in, automatically generated. There's a diagram showing them what routes are sent where. We've had NOC personnel just capture that in a screenshot and email it to the customer when they want to see it in a graphical manner. And likewise, our syslog has a Perl wrapper that color codes up as green and down as red, and substitutes in the interface description value learned as part of our regular MRTG configuration generation, so that when an interface goes up or down, the log entry has a local meaning by showing the customer's representation. So it's a little scrunched for the PDF, but you can get an idea. This is a sample of our automatic network diagrams for a customer in one of our cities. It shows the distribution router within our CO. It shows that in this case it's on router dist4, interface card S3x0, T1 number 7 and time slots 1 through 15. Shows the WAN network mapped from distribution to CPE, specific endpoint addresses for people to reference, and then whatever the customer's network is represented at the bottom, whatever their LAN block or LAN blocks are, the likely LAN gateway, even though from a distribution router we have no easy way of knowing what's going to be assigned, because some of the customers may choose to subnet further. And then these, on our MRTG page, are clickable links to give people a translation of what /28 actually means, so they don't have to have it printed out and taped to their cork board next to their desk. It's always available when they're looking at one of the most likely places they'd be looking at a slash notation. And if by chance there's any sort of extra admin distance configured on the router configuration, we have a table that shows all the different values within Cisco iOS for those distances. And if by chance there's an internal tag, which for us the only tags we're using is on our black hole server, we tag black hole routes as 666. But the hook is there to make it easy to show the staff what's going on. Likewise, here's a modified snapshot of our log watcher. Dist6 Dallas is our T1 distribution router in Dallas. And the other day, 1 in the afternoon, customer PM Realty and their location on Dallas Parkway must have had a 32-second outage, and another one that's about 30 seconds. So my suspicion is for one reason or another, their CPE got rebooted. The Adtran CPE that we often use takes about 30 seconds, at least from a T1 perspective, down to up. So it marked in here that the interface, in this case the line protocol, went down. Shows again when the controller and the interface comes up, a second reboot of some form. And so this allows our NOC to see what's going on a per customer level, some quick representation of what's important and what's not. We mark loopback messages. Loopback shows up in blue, and OSPF and BGP messages show up in yellow. Simple way for them to say, hey, is this important? Is it not important? Assuming that they're actually watching it, which can be potluck, but gives them the tool that if the customer calls in and says, my internet's down. Oh, yeah, your T1 went down about 4 minutes ago. Let us go ahead and investigate, and we can look a little bit more intelligent in front of the customer instead of having to go fishing around and figuring out what router they're on and look at some other representation there. So the usual plea here at NANOG, please prevent bad traffic. Do whatever you can to prevent spoofing. We use unicast RPF wherever possible. We have a stock inbound access list we use on all customers. There's actually two variations. One is for our legacy retail customers, where which blocks anything OSPF, perhaps a couple of multicast things unless they've requested a specific exemption, which we've never had any, and double checks to make sure that they never spoof anything that's coming from our interface subnets. We know where they are. That way, if for some reason the unicast RPF check gets removed, maybe Ceph blew up and we re-enabled it, but it wasn't enough to get the RPF check restored on the interface, we know that we're at least protecting against spoofing that would blow up our internal BGP sessions and so forth. All that gets blocked before it ever gets into our network. The second variation of the inbound ACL is used on our wholesale customers, our ISPs, and our colo areas, and that one's a little bit wider, considering the retail ACL also blocks the NetBIOS over TCP stuff. We take a stance that unless they've got some specific reason to share Windows files and printers wide open over the internet, they probably don't want that open. We block that on our retail side, but leave it open on the wholesale side. And as soon as you've got an opportunity to work it into your configuration, highly recommend some sort of black hole router. We've cannibalized a couple of console servers that also work as console servers, and there are black hole triggers. Take a look for RTBH in Google or whatever to find out basic ways of doing it. We've also built a very basic but very functional NetFlow infrastructure. So when we get DOSed, we know how to figure out at least who's getting targeted. Our normal recourse is to black hole the victim address first. It's the quickest thing for us to find in the NetFlow reports, figure out whether it's a very distributed or very singular source. So we'll then go back and check whether the source is singular or multiple, look for the largest attackers at least, and we'll black hole from the source, and then we'll restore the victim back to operation. So it's got minimal impact to the rest of our customers throughout the entire event, gets our customer completely back online as soon as we can, and starts black holing the source as quickly as we can. So that's my story. It's worked very well for us. I've told management that my goal is that the NOC can handle 90% of the issues completely on their own, another 9% of the issues with just asking me a few questions, and about 1% of the issues that I have to say, I'll deal with it. It's going to take me far longer to explain it to you than it will for me to resolve it. It's better for the customer to get the customer up and running and then circle back and train the NOC later. And we've truly gotten to that point and then some. I mean, my phone rings quite infrequently. The only exception to how often I get called is often on those where some other completely independent event is happening on the network, usually on the voice side or transport side, and a customer calls in with an IP-related question, and our NOC is too overwhelmed to handle it. They'll punt it over to me, and that's about the only exception to getting rare calls every 3 months or so. If any of you here in the room or later watching the archives are interested in any part of our configurations, please email me and I'll be happy to send you whatever snippets you'd like. At this point, I'm opening up to questions. Anything you want to see further, I can connect in and do some demonstrations. Any other questions you've got, come on up. Very good.